things asking me about my car's extended warranty, and you would also call that thing a robot. It's a, robocallers. Is that a robot? So the robots come in a lot of different, like the robocaller has no physical form, and the robots that are in like manufacturing plants they're like an arm on a base. They don't move though, and then you've got like something like this where this is a mobile robotics task. And so these slides and these lectures all kind of focus around that because mobile robotics introduces a lot of interesting problems that we have to overcome. And I think when you think classically of a robot, you're thinking of a mobile robot, one that's capable of moving around. And so once you have a map, and then you're able to move around in that map, you have some other questions like tracking your position in this map, where are you going into the map, how do you get there? And so, like in this image here, we see this like line, which this is a path that a robot has plotted from some starting position to some ending position. And how you generate that map, how to move around your environment, all these are actually very complex questions that have answers. A lot of these are solved problems, but one of the difficult things is how do you take somebody else's solved problem that may be used on, like, I'm gonna go back up here, like this robot. Sure, like this thing has software written for it that can have it navigate around a map. But what if I want to take that thing's software and use it on a robot that's completely different? It's the same concept, but one of the problems in robotics is that the implementations are so different from each other. You've got, the robots are entirely different, but they use the same concept. And so how do we make that code portable? How do we share it so that we're not constantly, reinventing the wheel every time we want to use one of these sort of we're trying to use one of these solutions in our implementation. And so that's where robot operating system comes in. Is robot operating system is a set of software libraries and tools that help you build robotic applications. Its name stands for robot operating system, and it's not so much like an operating system like Windows or Linux or Mac OS is. It's a collection of software libraries, and it's also enforces a communication standard. And so it provides like a bunch of algorithms for mapping, path planning, and all these different tasks we might want a robot to do. And one of the things that ROS does is, like I said, actually here's a good image, is all these are different robots, all very different in form and even different in locomotion. Like you could have robots that fly, you have robots that walk. But there are things they have in common. So, like if you're wanting to plan a path through your environment, they all need to achieve that task and then follow that path. And so the way they follow that path is through some forward motion. And that motion may be carried out by wheels, legs, or propellers on the quadcopter up there. So they all have that in common. And what ROS does is ROS will sort of provide a standard for how these robots interact with these different algorithms. So it provides interfaces to standardize robotics concepts. And the way it does this is through a messaging system that ROS provides. So we've got this sort of diagram here that's a very simple way to think about what ROS is, or at least ROS 1. There's actually a new version of ROS called ROS 2. It's very slow to take on, to be adopted, even though it's picking up speed. But all of this is going to be contextualized by ROS 1. And so ROS 1 has this sort of structure here where you have something called the ROS master. And the ROS master manages connections between different programs. And so those programs are called nodes. So we have this node here, this node here. These are two different programs. And they have this concept where they will publish data to something we call a topic, and then other nodes can subscribe to that topic, and every time there are updates to it, they get, as this diagram indicates, a callback message where they can receive that data. And so that's all the ROS lingo. I've got some slides that kind of go into that a little bit more, but I'm just going to leave this up here. So I think one of the things, whenever people first are introduced to ROS, is you may be confused by why this structure exists. Because if you've just done like kind of small robotics projects in the past, simple ones, you wrote one application that was your robot. It's just one thing that runs. But in reality, you've got usually a collection of computers that are running maybe on one computer, maybe across multiple computers, that are all working in collaboration with each other to achieve whatever the task is. And so we may have a program written in C++ that does path planning, and then maybe you've got another program written in Python that's doing some image processing, and then you want to, I don't know, pass that image processing data to the path planning node, and it'll tell you maybe if you see like an obstacle in front of you, and then the path planner needs to move around that. So real robotics, like more industrial level robotics, what I should say, is usually composed of multiple different programs all running at the same time, doing many complicated things, and they need to pass information between each other. And that's one of the things that ROS facilitates, is a standard way for data to be sent between different programs. And I think one of the best ways to understand this is just, we'll just flip over to my robot here, and we'll just take a look at it. So, on this, let me introduce this robot I have here. This is the TurtleBot 2. It was a very popular development platform for robot operating systems. A couple of years ago, it's been replaced by TurtleBot 3 and then now TurtleBot 4. So this guy's a little out of date. They stopped maintaining the software packages for it, and I'm not sure why, because the hardware is still perfectly serviceable. But what it's got is, well, on top we've got a little computer here. This is a Jetson Nano. That's also a little out of date. And it's running Ubuntu, a Linux distribution that has ROS installed. And from this thing, it's connected to this base here that's called a Kabuki. It's kind of like it looks like a Roomba, and it sort of is like one in the fact it's just a circle with wheels, and it's got a bumper on the front. And it also has some sensors internally that sense motion. It's got this base that's connected to this computer so they can send motion commands to it. And then I've also got an Xbox Connect on the bottom here, which is its depth sensor. This is a camera that reads, basically there's a point cloud in infrared that is sort of sprayed out in front of it. And that camera is looking for these infrared dots being projected into its environment. And then it's reading, it's getting distance information. So with that information, we can have the robot build maps of its environment and avoid collisions. And then of course it's a camera as well, so you can just recognize things in the environment. And so all these things are connected to the computer here, and then we're using ROS to interface with these. So that's one of the things that ROS does as well, is normally I would have to read from this camera data or figure out how to talk to this base, but ROS already has interfaces for these things. So I don't have to do the work of figuring out how to connect to these devices. All I have to do is use the packages that ROS has already created for me. So let me close out some of these, and we'll start it off from scratch here. These are all different terminal windows. Okay, so it knows that it's been disconnected from. So whenever we're going to run ROS, so typically the only thing you really need to do to get started is you launch
the ROS core. And the ROS core will start up and it will give me this message that I'm not sure that it's always giving me. Sure, it's not a problem. And once the ROS core is running, then you can launch other programs, or nodes as we call them, that will then communicate through the ROS core. So I could go through and I could manually launch other programs, but ROS often provides individual scripts that will called launch files that will launch the ROS core along with a bunch of other different nodes. So I'm going to use this thing called, I've got a command here called ROS launch, and then this package of turtlebot bring up, and then minimal.launch, and that's going to bring up basically just what this thing needs to communicate with the robot base. So if I do that, it's going to launch the ROS core, and then it's also going to launch everything, all the other programs that it uses for driving this base here. So we heard that little jingle, so it successfully connected. And so now all this stuff is running, and then what I can do is I'm going to come over to here, and I'm going to launch another node called keyboard teleop, which keyboard teleop allows me to send velocity commands to this robot from my keyboard. So
put it on the box, okay.
that's fine. It's not fast enough. It's not going to get away.
Famous last word.
I hope my reflexes are good enough that I would just be able to so I'm able to just kind of turn it around and stuff from my keyboard over here. Now what's actually happening with this is, let me get my piece of chalk. Is abstractly, I'm going to go over to this chalkboard over here just to sketch for a minute. Sorry.
My desk.
Is we have a program that's running the base of the robot. I'm just going to call it base for right now. It's not what it's actually called. And then we've got the teleop program that it just launched. And both of these nodes are registered with the ROS core. So ROS core is running. Both of these guys are connected to ROS core. But what we have is there's a topic called command velocity. What is it called? CDVEL, called command velocity. And teleop. Well, even before I started teleop, the base is subscribed to this command velocity topic, and then teleop publishes to this topic. So I give velocity commands to this topic, and then the base reads from it. And so that's every time I press one of the keys on the keyboard, we publish a new message to that topic, and then the base responds to it, or the program that is driving the base. Now, what ROS does with these topics is each topic has a message type associated with it. And I'll just pull up the page for that. There we go. Let's just look up ROS. Keyring. I'm on a network that doesn't have internet. I gotta switch back to the other one. Please. Yeah, sorry, this is all going to be a little rough due to technical issues.
Just ask us if you need to figure out it. Also,
Oh, it's not the router's fault, it's,
well, you can plug router in.
If you're on the air desk, I think 11311 is actually open.
So you don't have to run router.
it wasn't going to be an issue until it was. These are all workarounds. It's fine, we'll get through it. Yeah, anyways, ROS, twist message I'm looking for, so. Here we go. So this is just kind of, the ROS documentation. So on each topic, so we have a topic here that tells me velocities that I'm trying to command the base to use. And each topic has a message type associated with it. And this is where ROS standardizes interfaces in robotics. So the command velocity is of the twist message type. And the twist message type has this structure where we have two three-dimensional vectors, a linear and an angular vector. And what we're doing is we are populating this vector with the velocities that I want this robot to move at. And so then the base node over there receives those velocities and then has a control system that's trying to make this robot carry out the velocities that was commanded. And if we look at this, so down here, we'll see what a vector 3 is. Oh, sorry, question.
Is that like is the first vector like a translation vector, just a point space translation, and the second like a Euler angle, where it's x, y, z?
Yeah. So this is so each of these are. You're right. So one's linear, so you're telling it. Actually, I need to talk about how we represent the robot in from a geometry kind of point of view. But yeah, so we have linear velocities, and then we have angular velocities. So the way we model robots is, oops, let me just go back to the beginning here. So each of these are just a three-dimensional vector, and they contain velocities along different dimensions that I want the robot to move at. So the linear, what it does is this robot, I'll draw it over here. So let's say it's got some plates here, and there's its base. There we go. That kind of looks like the robot. So the way this robot is modeled is we say that it exists at a little tiny point in space, and then it has a reference frame. And so this reference frame is a three-dimensional frame that looks something like this that comes out from it. Yeah. This is X, Y, and Z. And so what the twist message does is it will specify some linear velocity that I want it to move at and some angular velocity that I want it to move at. So we have linear velocity, so this robot just has wheels facing forward, right? So when those wheels move, it just drives forward. So this thing only can really move along that x-axis in front of it. So when I publish a velocity to it, I'm really just telling it on this, it's a three-dimensional vector. But for this robot, it can really only respond to velocities that I publish along its x direction. So I'll tell it how to move like that. And then on this angular part, around the z-axis, I can specify how much I want it to rotate. So whenever I give it commands from this keyboard, I'm giving it some combination of linear velocity and angular velocity. And then with those two in combination, I can make it turn and travel in interesting trajectories. And we can see that because we can actually inspect what information is being sent across that topic. whenever this robot is running, we can actually, with ROS, let me just clear this. We can see all the different topics that are being published by using a command called ROS topic list. And all these are individual topics with information that's being published across them. Some of these are a little obtuse, I feel, but some of these are a little easier to understand. So let's see, we see, this one has a variety of command velocities, which is a little annoying. They got command velocity multiplexer.
It's probably infinite teleop.
Yeah, I feel like the older TurtleBots, I'm dating myself really quickly, used to just have one called command velocity, and then I guess the newer ones have made it better by making it more confusing and more detailed.
Is that not just the mobile-based command velocities?
Yeah,
I mean, it's not command vowel, but.
yeah. I mean, well, we can expect to find out. So I could say ROS topic info, and then we can specify CMD. Mux, and then we can say what was it, teleop. Put. Then we've got teleop. Okay. Oh, okay. Well, this is semi-intelligible. So looking at its info, we can see that it is, and I don't want to see if I can't. I've never tried to zoom in a terminal window. I'm not even sure.
Control plus.
This could control scroll just
Control plus.
Control plus, does it?
That thing.
No.
Control shift plus.
I know that command plus works on that.
Oh, no, control shift, that does, oh, thank you. Alright, cool, so that should make it a little visible. Yeah, so looking at this, we can see that it is of that type, twist. We've got, its publishers, so we've got the keyboard teleop, node that I was running, and then we can see this is subscribers to it, which is a word that I apparently can't say. And, so we have the mobile-based nodelet manager, which is kind of like the base that I wrote over there. And then ROS topic, I'm not really quite sure what that other thing is that subscribed to it.
That's your ROS topic list.
Oh, yeah, that makes sense. It shows up as a separate node.
Yeah.
I guess that makes sense. So anyways, we can see who's publishing and who's subscribing to this particular topic. Let's see, we can also look at what's on that topic. So let's see, say ROS topic echo. And we look at CMD, Bell, Mux. It's a little slow. Oh, yeah. There. So let me split this into let's separate. Thank you. Okay, so now if I publish something to it, we should see there we go. So I'm just telling it something to go along the x axis of velocity. So you'll see that kind of, actually, there we go. So it's commanding 0.2 meters per second as a linear velocity. And if I now tell it to turn to the left, we'll see along the z-axis a rotational velocity published. And so this is really, I think, one of the best examples of how ROS standardizes communication between different types of robots, because velocity is a very abstract concept that almost any robot is capable of adhering to in some capacity. Now, some robots obviously have their limits based on their kinematic structure. So this thing isn't going to be able to respond to if I told it to move linearly along the z direction. It's not going to just take up and fly. So, so you have a limit to what certain robots can respond to, but otherwise it's pretty abstract. So I can take messages, if I were to write a program that's going to command a robot to move around, and I tell it to publish twist messages, then any robot that can respond to those can then work with that application that I've written. So it's more modular and it's more portable that way. Something else ROS provides us with is tools for visualizing our robot, like what our robot sees and the sensory data that it takes in. So, I'm going to pull up another tab here, and then I also need to make sure this is running. I have another launch file. What I'm doing here is I'm just starting up the depth camera. And, uh-oh. Don't do this to me now. You've been so good all day. Unless I started it in a different tab, and so let's start back up again. Sometimes I have had the Xbox Connect can be a little funny. Yes. Connecting. Oh, maybe it'll just magically connect. I'll come back to you. Let's see. So I'm gonna pull up. Where is it? There. All right. So there's a tool called ROS that allows me to visualize what's going on with my robot, based on reading its published data across these different topics. So over here, I've got these different representations of the robot that are being constructed from the different topics. So what I want to demonstrate is this laser scan topic that's not publishing anything right now because you can't talk to me. Oh my god. They can't talk to the Connect, which is the Connect's not connected. At least there's a rational explanation. It must have disconnected when I carried it over here. All right, there's a little. All right, come on, buddy. I don't think it's going up.
It says meeting, but.
I have zero faith that it will find it. I will restart it, and I think it has a better chance. Don't tell me that. Okay, hang on. We'll start. Yes. Okay, you're still good. You're still, that's fine, that's fine. Okay, so 3D sensor. Hey, there we go. All right, and then RViz. Oh, you can see it it's because it's looking very far off into the distance. I mean, actually, So you can kind of see, I mean, so what we're looking at here is the depth camera, like I said, produces this field of infrared dots that then it tries to read the depth on the camera. A lot of robots want to use LiDAR data for different algorithms, so that's typically like a sort of linear scan of data in front of it. And so what we're doing is this thing is spoofing the output of a LiDAR by taking that depth map and just looking at a little slice of it. And so that's what we're looking at right here, and we can see as I move stuff in front of it, there we go. You can kind of see the chair is in front of the robot right now. And yeah, so we can see what the robot is seeing on the data that it publishes. So you have these tools like RViz that makes development a little easier because you can debug it. This image isn't very impressive, but I think it's kind of because the Kinect is not a very impressive sensor.
It should also be publishing on depth cloud or point cloud. Right?
It does also publish those.
So that might be a better thing to look at.
Yeah, we can look at, let's say we'll get this one. We can actually see the image associated with the depth. Look at that, isn't that great? Do you wonder why the Xbox Kinect was not a successful product?
Empirical data.
It's not calibrated actually. It's a problem, and that's why this thing looks like garbage as well. So I shouldn't rip on it that hard. What it did do successfully was give me a $12 fake LiDAR that I can buy. So you know, it's good for that.
It's better than the real sense, which is what, 230 or something?
Yeah, I mean, I guess that's not really that expensive, all things considered. But anyways, yeah. So you have tools like RViz that are subscribing. Oh wait, do I have is that one the proper point cloud? I don't know what topic the point cloud is on, so I don't know what these are mapped to. Typically, the way RViz works is when you first open it up, there's nothing in here. And what you can do is you can go to this add button here, and you can add different types of data according to different topics. So, if I were to add, actually maybe I can find the point cloud, so I can add a point cloud, and then I can go in here and try to associate it with a particular topic. So here I can find my list of topics, which either I'm impatient or that drop down menu is not working. Add by topic. Yeah. Oh yeah, you're right. Yes, we can also add a topic here. So, depth points. There it is. Maybe we got too much other stuff going on here. Let me turn off all the other ones. We got nothing.
Unreliable check.
It probably is, because that's probably the timestamps.
Well,
Yeah, that's what I know.
you know, honestly, this is just kind of par for the course at this point, because I've had a wild time preparing this stuff.
Check for reliable. It's probably time syncing, this sync, desync.
Yeah. Anyway, so RViz, so typically it's blank. You have to add things that you want. You don't always get this pretty 3D model of your robot as well. This is something as well that you have to structure and put in there. But you can work without it. You can actually, if you don't have a model of your robot, you can just see its frame of reference, like what I drew over here on the board. Float things. You could just import like how the robot is positioned and visualize that if you were writing like code for your own robot from scratch. So let's see. The other thing that I had prepared as well was a demonstration of some of the software packages that ROS provides. One of these is, to echo back to the slides, is something called G mapping, which I guess I'll just pull up some references of what it looks like. And that's right, I don't have internet on this thing, so oh my god. show you a picture of it because I'm anticipating it blowing up unexpectedly. Let's go over here. So GMAP. So if I wanted to build an autonomous mobile robotics application, one of the first things that I need is a map. And we can build maps with ROS using something called GMapping, which is a type of SLAM algorithm where it's simultaneously localizing and mapping in its environment. So what GMapping will do is, I didn't include a picture here. Somewhere there's a picture. Yeah, Google's gonna find me there we go. That's a picture from like RViz. Perfect. So we can kind of also see the robot as it's like moved around in here. But what GMapping will do is it will generate like a map like this. So using the laser scan, it will collect all the distances that it sees around it to build up what we call an occupancy grid. And then it will also track where it is in that environment, and these mapping algorithms are also tracking things that we refer to as landmarks in the environment. So anything that's easy for the robot to recognize over and over as it moves around in this environment. And so it'll track these landmarks, it'll track its position relative to those landmarks, and then it will take its laser data and then populate this map that we see here. So we can tell, what spaces are free for us to move through and what spaces are not. And so then once we build a map, then we can import that map into other algorithms where we can use them to navigate through the environment, or we can use them to mostly navigate. I don't know where else I was going with that. So let's see if we can run this on the turtle light. I installed it and I ran it earlier, and I don't know. Let's see if ROS actually shows it. Now, what's not great is the fact it's just floating up on top of this table. So, yeah, I'll try it anyways. Alright, so I ran this earlier and it didn't blow up. You can have a little bit of errors as a treat. That's not a good one. Process has died.
You check the log file.
I'm not checking that log file. That log file looks like insanity. Oh wait,
Is it because you're running
it's because of. Does it not want me running? Oh, maybe it is. It tries. I guess that. So these launch files are spinning up a bunch of nodes at once, and so I guess this one is also trying to simultaneously. Yeah, it's probably also trying to open the connect simultaneously. Okay, yeah, that's what it was trying to do. We had conflicting things running. The point cloud too, it's suddenly wow. So weird that it just wasn't earlier. That's I'm desensitized to it at this point. Let's see if we can add a map to this. There should be a map topic that's being generated. Oh my god, I think it's all coming together. So now, if I had my actual everything set up the way I wanted to, I would command it to drive around to build the map. But I'm going to push it. So, and we can see an update on here, which is pretty cool. So as we move around, and let's get rid of Point Cloud 2, even though that was very, very cool. But, oh, and it's actually Death Cloud. Anyways, yeah, so as I move this thing around, so you'll notice it is, as I push it, its position is being updated here. That's because we have motors and inertial measurement units built into the base here, so even though I'm not giving it a command to move around, it knows it's being pushed around thanks to those sensors. And so as we push it around, it's sort of building out this map.
You could go back on that, I think. Yeah.
And if I wasn't tethered to this table, this would be a lot more interesting. But we can continue to move this robot around and we'll try to map out the environment. And it probably doesn't see anything, and that's why it's not. Because even though you guys are out there, sorry, the control system doesn't like what I'm doing to it. Anyways, yeah, I should just be.
If you should laser scan, it might help to.
There we go. Alright, okay, it populated. But anyways, if it was on the ground and it could actually see the walls, we would be able to build a map out of this room. And then once we're done with that, we could then save that map and then have it, we could give it waypoints to navigate to these different points within the room using the built-in path planning and path following algorithms that are built into, or not built into, but part of the sort of ROS conglomerate. And then we have the robot move from point to point, which is in the end what I was planning on doing, but I can't really do that tethered to this table, and had numerous amount of problems that kind of delayed my progress on this workshop. So in the end, ROS has a lot of tools, and they help us build robotics projects without having to build everything from scratch, because it's actually like this G-mapping application that's running right now is incredibly complex. And to write something like this on your own is very difficult, especially to have something that works as robustly as it does. And you can just use G-mapping on any robot that has a laser scan and odometry information. So that's what's published from the robot. As I pushed around, the base publishes twist messages that are this odometry information from it moving. And I guess this is where I'll stop my talk, because I've kind of ran out of the material that I prepared or the material that worked. And if you have any questions, I'll just try to answer those. Do you have any questions right now? Oh, yes.
So I guess this is sort of a tangential question, but when you were passing the commands over to the bot, I'm supposing that's going through USB.
Yes, so the way it's exactly architected is this base node over here, you're right, it is speaking through USB, but that communication is handled from just this base node. So this base is then talking through USB to the Kabuki base. And the Kabuki is not, it's just its own like kind of random robot. It has its own sort of random set of commands that it responds to. And this base is what's publishing or not publishing, but managing the commands and the reading the sensor information, all that stuff through the Kabuki through USB. And then the base then publishes that sensory information back to the rest of the ROS network here.
Okay.
So yeah, so this thing's kind of doing its own thing and then providing a ROS interface for everybody else.
Got it.
Yes.
And then I guess sort of on that, how does it send the commands? Like what is the format? Is it like a bin file where it's just binary commands, or is it like sending, a series of like bash signals, or?
So what it's doing, so we're going to get into that with better technical detail next time, because we're going to actually build and programs that publish our own messages. But basically those, the messaging is facilitated by the ROS core. But what you get is in C++ and Python, which are the two main languages that are used in ROS, they provide APIs that you can call that then publish the messages. And they also will have structures that already are, like if I want to publish a twist command, there's a structure that can populate that has those three, those two, vectors inside of it, those, yeah. What am I trying to say? Three element vectors. Sorry, I had a, brain fart for a second. Yes.
So I see there's antennas on top. Does this have like IP connectivity?
Yeah, so I've got it set up on this, this router, and the thing that I really wanted to demonstrate was, the ROS core is currently running on this device, but I can actually, if I have my network set up correctly, I can run applications on, say like a laptop here, and they can read the messages being published by ROS core on different computers, and then they can publish back to it. So what ROS also allows you to do is distribute your computational load across different machines. And they all are interfaced through just like a TCP/IP connection. Yeah. Thank you for that. That's a good point. Yes.
Can we connect on the other end or
No, I can't even get it connected on to my laptop. It's mostly because.
Nine Wi-Fi guest usually supports it.
Oh, the guest list?
The guest list.
Oh, well, maybe they're over here. Honestly, I had no intuition to test that after.
11311.
Yeah, that's right.
Also, if you're doing stuff with sort of robots, the Grid router has everything on it.
This router I have is nothing special open, but the problem. The reason I couldn't demonstrate that today is, my laptop here is a Windows laptop, and I've got virtual machines on there, but I didn't get the, they have like a virtualized network interface that I have to then deal with, and I did not get all that sorted out. Yeah, well, it didn't work on one of these anyways. I can't get it because despite how this may have gone, I actually poured hours into this, and now I will share my grievances with you, which is the TurtleBot is a deprecated device that works with Ubuntu 14 and an older version of ROS, and then you got the NVIDIA Jetson that is also a deprecated piece of hardware, and it works with a different version of Ubuntu that is newer, but still older than other versions of Ubuntu that you'll find used commonly. Because now we're like, it's either 20 or 22, or like the versions you'll see people use now. This thing runs 18, and this thing, the TurtleBot, was last officially supported on Ubuntu 14. And it's just, everything is just old, and they're all different versions, and everything's like, it was a giant mess even getting this much to the community. So, yeah. Well, we showed you something. We got a map, which is honestly better than I thought this was going to go. So, any other questions? If you want to play around with it afterwards, feel free. I'll come up here and explore whatever I've got working as well.
I've got it.
What?
Communication with it.
You were able to connect?
Yep.
Can you publish a twist command?
Actually, I got spotted earlier. The RQT random Python one. That was me.
What?
That checked out, yeah. The
ROS
ROS topic we were trying to figure out what it was.
When there was a random topic there, that was me.
Okay.
That's why it was a different IP address.
Because I said that it was, and then I was looking at the message more, and I was like, that's not right. That's a different IP.
Yeah.
Someone else knows. And I never figured it out.
Yeah, I was like.
I was wondering when it was getting questioned.
Yeah. Anyways, all right. If there's no other questions right now, I guess we can stop the recording.